Okay, so it looks like it's working with the streaming. So we'll go ahead and re-import. Okay, now it's working. Yep, it's interesting how electricity was a commodity. Water is a commodity. Gas is a commodity. Now internet access is a commodity.
It'd be hard to live without internet.
Hmm?
It'd be hard to live without internet. Just in general, like how would you get a job without internet?
Go give them like a resume.
Most places won't
Yeah. Yeah, but
won't
everyone has an
accept
application.
anything
Everyone's
until
looking
you
for
filled out their application.
Yeah, I mean, I've tried doing like physical, like none of them are taking physical anymore.
Yeah, no, again, remember when I had
If
last
there's no
job, like,
internet, they will have to though.
Yeah, they will have to at that point. It has to.
No internet for you, maybe. Companies will always have internet.
But you have to keep in mind, not everybody lives in a country where the internet is reliable.
Yeah.
Yep.
And there's still a statistic of people that don't have internet at all.
Okay, so everything seems to be working. So we'll go all the way to the end, being so optimistic that the program does work. So we see how the stack pointer is balanced, and the halt instruction is online at location 25, and I think it is. Okay, so I'm pretty sure we are at the correct point. But how do we know the swap actually occurred? Because the swap subroutine can just return, right? Then everything is balanced and everything looks good. So we have to look at those locations, and that's on column C. So what we do is we look up column C and we see that FE, which is X, has a value of 3. FF, which is Y, has a value of 7 to begin with. This is at the beginning of the program. And during the execution of the swap subroutine, okay, we just kind of skip all of the other items, being optimistic. This is our local variable t, okay, that I was using as the return address and causing the program to continue execution at location 3. And now we can see FE, which is X, is getting a value of 7, which was the value of Y. And then Y is at location FF is now getting a value of 3. So the swap operation is confirmed to also happen the way it's supposed to. So you can see how the trace is kind of helpful because you can go back and forth. Once you get past a certain point, it's okay. You can just kind of scroll back and see how you got to that point. So are we okay so far with the explanation of the swap subroutine and kind of the process of writing the code and debugging the code? Okay. Are there any questions about the Fibonacci program that is due on Thursday?
You are assuming we have started.
Well, if you have not started yet, okay, it's not necessarily a really bad thing because I can give you some pointers of how to get started with that homework assignment. Okay, so we'll go ahead and work with that one a little bit. Okay. All right. So this has to do with the assignment that is due on Thursday. So you might be pushing a little bit for time, but it is not doable. Okay. So I'm gonna just rewrite the Fibonacci program here and give you the original code, and then I'll give you some recommendation of how to do this. So if n is less than 2, we return just n. Otherwise, we return f of n minus 1 plus f of n minus 2. And that's the code that you are supposed to implement. Okay. This code is compilable, okay, which means you can actually plug it into a C program, compile it, and then use GDB to run it with breakpoints and try to understand how it works. Okay. But because there's only one statement in F, it makes it kind of really troublesome to kind of break apart. Am I dealing with the first call or the second call, or am I returning? Because they're all on the same line. So the way to kind of make this a little bit easier to understand in terms of how the recursion works, so that you can actually understand what your program is supposed to do when it comes to the recursive part of it. This may be a slightly better way to kind of help yourself understand the code. Okay, so I'm going to have a local variable x here, and I'll explain why x is kind of a good thing to have. So I'll turn the ternary operator or the ternary expression here into a full, conditional statement in C. So we say when n is less than 2, else, okay, open and close, and then we return the local variable x. So I'm not going to return inside a control structure. So in this case, if x is less than 2, okay, x gets n. Otherwise, I'll even break this up into 2 steps. So we say x is f of n minus 1, and then we say x plus equal to f of n minus 2. So I'm even separating the addition of f of n minus 1 and f of n minus 2 into 2 separate C statements, so they can put a breakpoint on each one to separate, am I calling it the first time or am I calling it the second time? Okay, so this particular representation of exactly the same logic is easier to visualize and easier to understand if you want to use a debugger to help you understand, okay, where am I going from here? Okay, we go from here to here and here, okay? So are we doing okay so far with this code? So once you have a full understanding of how this code is supposed to behave in C, then you have to implement it in assembly. So how do you implement it in assembly? Well, you don't want to do the entire thing all at once, okay? So you might want to do it kind of in this way. So I'll give you an idea of how I would step by step work on this particular program. And you don't have to do it this way, okay? It's just that if you want to do things really, really step by step, okay, do it like this first. In other words, do I know how to access a parameter, and do I know how to return the parameter itself? Okay, that should not be very difficult. Okay, so once you can do this, then we'll put in the conditional statement. So then we'll have the next version, which is very much like the one that we already have, but no recursion. Okay, what we'll do is we'll say, if n is less than 2, else I would not use a local variable because that just kind of complicates things without a necessity. So we'll just go ahead and do it kind of not so nice way, okay? But I don't want to do it recursively. So just pick a particular value that is unlikely to happen by itself and return it. Because at this point, I just want to make sure that I can test whether n is less than 2. If n is less than 2, whatever n is, which is either 0 or 1. If n is not less than 2, I return a constant of 147 just to confirm that the conditional statement does work. Okay, because I want to know whether I can get to the right branch or not. Is that okay? All right, so if this does work, okay, then we'll go one step further and we say, okay, if that works, then we'll do one recursive call here. Let's see if I do it this way. I'm just thinking in terms of whether you can confirm the value that it returns is correct or not. So if you do it this way, okay, what would be f of 3? What is going to be the return value of f of 3? So you have to kind of think about it a little bit, okay? F of 3, okay, 3 is less than 2 is false. We go here. We now look for f of 2. Okay, this is one level of recursion. N is 2, 2 is less than 2 is false. We go back here. Now we look for f of 1. Then we get back here. 1 is less than 2, return 1. Good. That 1 is returned back to the second invocation, which is now returned to the second invocation. So the whole thing will return just 1. Okay, even though it is recursive, it is just going to return a value of 1. Is that making any sense? Okay, so you can check that first. Okay, now if you want to check whether your whether multi-level is working or not just because of the return value, you can just add a constant to f of n minus 1 so that each level of recursion is going to add 3 to the result that you're getting. Is that okay? So f of 3 is going to be, I think it's going to be 7. Because it will take f of 3 has a plus 3 itself, and then f of 2 has also another plus 3, and then f of 1 is just going to return 1. So it becomes 1 plus 3, which is 4, and then 4 plus 3 is 7. Is that okay? So do a single point of recursion first. Confirm that your single point of recursion is working. Then you add the second point of recursion. So when this is working, okay, then you change the constant of 3 and change it to f of n minus 2. Are we doing okay so far with this? All right, cool. So that's kind of how I would structure the process of developing this program, is to do it step by step. Okay, because if you do it in one single shot, write all I think it will take maybe 50 lines of code or so. Okay, if you write all 50 lines of code, which is not a whole lot, okay, but there's complexity in that 50 lines of code. So a lot of things can go wrong in that 50 lines of code, and debugging 50 lines of code, when they're not tedious but actually kind of tricky code to write, is not easy. But doing it this way, you're making a transition from one version to another version in a way that is not too much, okay, between the revisions. So that might be better, okay, depending on how confident you are with your programming skills. It's not so much programming as it is debugging, really. You can fully understand all the concepts in this class, but if you throw in one bug, how fast can you find that bug? That really is, kind of a big factor. So are we doing okay so far? Are there any questions? Yep.
Do you have any tips for how to add the two values together?
Huh?
Do you have any tips for how to add the return?
Okay, so I'll give you a different program to think about. Okay, so we'll go ahead and, I'm not sure whether we have talked about this already, so you guys can tell me, because I cannot remember. I remember doing this in one of my cisp310 class, but not in this class. So do you remember the subroutines with Johnny as a name? No? Okay, well, we'll do it this way. So here's a subroutine. It returns 5. Okay, one person's getting it. Very good. Okay, another person's getting it. Okay. So this one is returning 7. No one's getting this one? No? No? No one is getting this one? Jerry Ryan is the actress who played the character 7 of 9 in Star Trek Voyager. Okay, so now we have U in 8, 12, okay? So how do I get to 12? Well, we add those two. So we return Johnny and Ryan, the sum of the return values of those two. So now the question is, how do you do this? The implementation of Johnny and Ryan is super easy, right? You just put 5 into register A, do the usual return sequence, you're done. You put 7 into register A, and you do the typical return sequence, and you're done. So the difficult part is, well, how do I compute the sum of Johnny and Ryan? So there are several ways to look at this, okay? Depending on how you want to do it. So one way to look at this, and I will consider this as a correct solution, is really to use a local variable of some kind. Let's call it x. So we say x is the return value of Johnny, and then we add the return value of Ryan to x, and then we return x, then we're done. So if you translate this C code into assembly code, making use of an explicit local variable x, it will get the job done. So that's one way to do it. Definitely will work. Is that okay? But that means, well, when I say that, that means, well, there's actually a way to make this work without the use of an explicit local variable. Does that make any sense? Okay. So how do we do it? So we'll just focus on this version at this point. Okay, so we say 12, okay, as the entry point of the subroutine. I'm kind of mixing assembly code and C code right now. I'm just not gonna open another window to do this, okay? So we'll call Johnny first, okay? That's it, that's inevitable. We have to call Johnny. So we'll do the usual stuff, okay? Decrement D, LDIA with .5 plus, STDA, JMPI to Johnny. And when it does return, there's nothing to deallocate because Johnny did not require any arguments, so there's nothing to deallocate. So by the same token, we also know how to call Ryan. So don't copy this because I'm gonna have some code to insert in between. Okay, so call to Johnny, call to Ryan, not a problem. The problem is at this point of the execution, register A has the return value of Johnny. But when we call Ryan, register A is going to be overwritten to become the return value of Ryan. Okay? So we have a little bit of a problem because before I can make use of the return value of Johnny, I would have lost it already. Okay? So now the question is, how do we save the value of the return value of Johnny? So you might say, well, we'll copy to another register. Okay? But that's not going to work in general because there's no guarantee how many registers A, B, or C that a subroutine might use. So just because your subroutine does not trash a particular register does not mean that somebody else's implementation of that subroutine would not do the same thing. So do not make the assumption that a particular register is untouched by a subroutine. So this does not work. So where else can I save the value of register A? Onto the stack, okay? So we push it on the stack. So we decrement D, we STDA. So this way we are pushing the return value of Johnny on the stack. Once it is on the stack, unless some other subroutine is doing something wrong, it will remain on the stack, okay? So at this point, okay, when we get back from Ryan, register A has the return value of Ryan, and then the return value of Johnny is on the stack. So what we need to do is now we go retrieve it. So we do a load into register B, cannot use register A because A is already useful. So we retrieve it here, and then we increment D to deallocate it on the stack. In other words, we pop the return value of Johnny into register B. So now we have register A containing the return value of Ryan, register B containing the return value of Johnny. I got both of them. So now we are just going to add those two, and then we have the usual return sequence. Okay, don't mess up register A. Make sure because it is supposed to use register A to return the value. So now we can just do a LDBD, increment D, JMPB. That's it. So by dynamically using the stack to save the return value from one function call, we can then use it later on. Okay. So in your program, it's going to complicate just a little bit because after you save the return value of the first call to F, you would have to push the argument for the second call. Okay, so you have to pop everything first, then you can go back to the saved return value of the first call to F. But the trick is to use the stack to save a return value. Okay. So we got 5 minutes left. Okay. So with 5 minutes left, unless there are more questions about the Fibonacci program, I'm gonna give you an idea of what I'll be talking about on Thursday. Okay. So on Thursday, obviously, I'm going to talk about the solution of the Fibonacci program. So I'll be doing it on the fly during class time. Hopefully, we'll introduce a few bugs into it so I can show you guys how to debug a program. I think it's one of the things that we do not put enough time into, in general, across all the classes, is how do we debug programs? We talk about all the concepts in C++, in Java, in this and that and whatnot, but how do we debug a program? That is usually not touched on too much. But there are other things that we'll also be talking about. Let me go back to, where is that? Which one? Okay. So we go back to the main modules. So Thursday is going to be a fun class because on Thursday we are going to go to, where is that? Keep going, keep going. We're going to play with hack1.stripped, okay? It's kind of a balance. I do want to get to structures and pointers, but this one is fun because we can do it now. So on Thursday, I'm going to hack a program. This, by the way, if you download it, you can run it in AMD 64-bit Linux. It's an executable. You can actually run the program. But I'm going to hack this program. Okay, the program has a protection feature where if you do not know the password, it won't let you access the full version of the program. Okay, so I'm going to show you guys how to hack the program so that I can gain access to the things that I'm not supposed to have access to. And in that process, hopefully, we'll also be able to explain how the stack is utilized in a regular C and C++ program and how exploits happen. Okay, in other words, how not to write a particular program. Okay, so it's going to be fun. Okay, I think on Thursday we'll get to this one. We'll be talking about instruction for the Intel processor. So it'll be different mnemonics compared to what we use in this class, but I think for the most part they are still understandable. Okay, especially if I explain that. So there will be some new instructions that I'll be introducing. It won't be on the test. Okay, the final exam is not going to have anything like this, but I do want to demonstrate it because that is one application of this class. Okay, is for people to truly understand what is going on when the C++ or C program executes, and either be on the white hat side, okay, to help people understand why not write a program in a particular way, or if you so choose, okay, and it will be at your own risk to be on the black hat side to crack programs. But then you'll be assuming the responsibility that goes along with that. Yes.
What does next week look like?
So next week, we only have classes until, the 12th? What's the last day of instruction? Friday? Okay. So we'll definitely review for the final exam. So there'll be one class where I will give you, I'll go over a previous final exam so that you guys have some idea of, in past semesters what that looks like. So there'll be one class for that. We'll definitely get to structures and pointers because I think it's important to get to structures. We have already used pointers, so that's not a big deal. But structures is kind of an important thing because we want to kind of get some understanding of how structs or C++ classes are represented internally in memory. So we'll get to that a little bit. Yep.
So what's the final exam going to focus on?
The final exam is going to focus on everything after the material that is not covered in exam 2. But it is not comprehensive because I cannot say anything like, oh, you don't have to understand the flags anymore. Or you don't have to understand registers anymore, or you don't have to understand the processor architecture anymore. It's just that the focus is going to be on subroutines, how we use the stack, how we pass parameters, how we return values, that sort of stuff. So that'll be the focus. You still need to remember some of the stuff like, signed comparison, unsigned comparison, two's complement, that sort of thing. I'm still going to assume that you remember those things. But it will still be open book and open notes. So you can bring anything. You can even include all the stuff that you brought along in exam 1 and exam 2 in the final exam. Okay, so are we good so far? Okay, so I'm not going to give you guys any new assignment right now. So the only assignment that is still active is the Fibonacci one. Yep, go ahead.
When is final?
When is final? Okay, thank you. Now the question is, which Tuesday?
Next Tuesday.
I think so.